In this video, we are going to use the quotient rule to take a derivative and figure out where a function has a critical number, relative extrema, and where it's increasing and decreasing, all without a picture. So we're going to use the derivative to find this information. The tough part is the fact that it has x's on both the top and the bottom. So when I go to take this derivative, I will use the quotient rule. And so I'm going to start with the derivative of the top. Derivative of 1x is 1. The original bottom is x minus 9. Minus, for quotient rule, the derivative of the bottom. Derivative of 1x is 1. Derivative of negative 9 is 0. So the derivative of the bottom is also just 1 times the original top is x. All over the original denominator gets squared. X minus 9 is squared. So in trying to find any critical numbers, I want to see what makes the numerator 0 and what makes the denominator 0. So right off the bat, the denominator x minus 9 is going to be 0 when x is 9. That makes the denominator 0, so we're making the derivative undefined. I'm going to have to do some work to see what makes the top 0 though. So this numerator here, I want to see what makes it 0, so I'm going to distribute this 1 to x minus 9, which is going to be x minus 9. And then we have minus 1 times x is just a minus x. So I'm simplifying my numerator to see what makes it 0. Well, I have x minus x, which is going to cancel, so I just get negative 9, and I want to set that equal to 0. Well, negative 9 is a constant. There's nothing that's going to make that 0. So my simplified derivative ends up being negative 9 over x minus 9 all squared, and it has one thing that can make it 0 or undefined, and that is x is 9 from the denominator. The top can't be 0, but the bottom can. Negative 9 is never 0, but x minus 9 is when x is 9. Is it a critical number though? So we're asked for critical numbers here. Critical numbers are any numbers that make the derivative 0 or undefined, but also go into the original function. So it has to be within the domain. So I'm going to check if this is a critical number or not. I'm going to plug in 9 to the original function, this x over x minus 9. So plugging it in, I would get 9 in the top, and 9 minus 9 in the bottom is 0. We get 9 divided by 0. This is actually a number over 0 tells us this is a vertical asymptote, so there are no critical numbers. The one and only place that could have been a critical number because it gave us an undefined derivative doesn't go into the original, so it's not called a critical number. And with that, I already know there's no relative extrema. Relative extrema can only occur at critical numbers, and we don't have a critical number for this function. Our one spot that made the derivative undefined ends up being a vertical asymptote, so it's not going to be a relative max or min. It's going to be going off to infinity or negative infinity without bound, so there's not a place where it stops, and the highest y value is 10 or something like that. We're still going to use it the same way we would if it were a critical number though. I'm going to put it on my sign chart first. It's special. It makes the derivative undefined. And I'm going to test number to the left and to the right of 9. So testing a number to the left, if I plug in 0, on a sign chart, you're always plugging into a derivative. So plugging in to a derivative, I'm going to plug into the simplified form here. The numerator is negative 9. The denominator, if you do 0 minus 9 squared, you'd get negative 9 squared. Any negative number squared is going to be positive. So a negative divided by a positive, this function must start off decreasing before that vertical asymptote. After 0, I can plug in anything. I might just plug in 10, or after 9 rather. Or you can plug in any number. I'm just going to plug in 10 to the derivative always, not the original function for a sign chart. The numerator is negative 9, so it's always negative. The denominator, 10 minus 9 is 1. 1 squared is going to stay 1. So negative divided by a positive is negative. We're going from decreasing to decreasing. There's no sign change to give us a relative extrema. We also know that it's a vertical asymptote anyway. So if we wanted to sketch what this graph looks like, which is a tricky thing to do, but this graph has a vertical asymptote at 9. So here's 9. I'm going to put my vertical asymptote. And it's decreasing before the vertical asymptote and decreasing after the vertical asymptote. So decreasing everywhere except for at 9 where the derivative is undefined. So if we think in terms of negative infinity to positive infinity, we're going to write these intervals. It is increasing nowhere. There's no increasing intervals, but it is decreasing negative infinity, not to positive infinity. It's going to stop at 9 because it has an undefined derivative. Negative infinity to 9 and 9 to infinity. Before and after 9, the function is decreasing. So there's an example with the quotient rule. I have other examples where we have chain rule and just some basic derivatives to do these sign charts with.